Hello everyone, welcome to the video lecture series on Simplex method. I am Mayur Gohil. I shall be dealing today with what is a general linear programming problem and how it is to be dealt with. So let me help you out what is a linear programming problem in general. So linear programming problem in short is written as LPP and in general is given like in general is given as optimize z. Now this z is a function that we are supposed to maximize or minimize. Right now I am writing it optimize. So here it is like c1 x1 plus c2 x2 plus and so on up to cn xn, subject to constraints. We have some constraints will be given to us. So let's say a11 x1 plus a12 x2 plus and so on up to a1 n xn less equal. Now here there are options are there, less equal or greater equal b1. Now this is the first condition. There can be anything given here, so I'll put it in some bracket over here. So that is one thing. Then here you have a12 no, yeah, a12 now. So a21 x1 a22 x2 and so on up to a2n xn. Again the same situation arises, less than equal greater equal b2. So and this goes on up to am1 x1 plus am2 x2 plus and so on up to amn xn. Okay, and then again here there is less equal greater equal, or here there can be bm. Okay, like this. So all these conditions are there, and then another conditions are subject to these constraints, and there are few more constraints that are called here, or which are x1 x2 x3 up to xn. They are greater equal to 0. Now this is the general form of the LPP. Okay, this is the general form of the LPP that you see. Now I would like to tell you what all details are there. These each set of equation has a name and it has its own meaning. Okay, the first one is called the objective function. Okay, I'll just write here the name. It is called the objective function. These m equations that you see, all these are called constraints. Okay, these are called constraints. Okay, then these one at the bottom that you see, these are called non-negativity constraints. Okay, so these are non-negativity conditions or constraints. So this is basic form of the LPP that you see over here. Now this LPP is what further, if you write it, this is called the canonical form. Okay, this itself is the canonical form, and later on when you see it in different formats, then you will get a different meaning of it. Okay, so the given format, okay, this what you see here, the general LPP itself, whatever is given to you, is itself the canonical form. So we will see it in detail, but then you can consider this itself as a canonical form. So here I'll just give this is called the canonical form of the LPP. Okay, linear programming problem. Now the above linear programming problem can be written in much better way using some compact notations and some matrix notation. So I'll just help you out how it is written in short. So the general LPP in compact form can be expressed as follows. I'll just label this compact form, and here canonical form also I'll label so that you remember. Can be expressed in the compact form as follows. So the first thing, the optimization function which we wrote, so optimize, when we write, it means either there is a maximization option or there is a minimization option. We don't know, it depends upon the question. Okay, some specific question will be given to you, so here it will be maximization or minimization. Z equals to summation Cj xj, where j runs from 1 to n. Okay, and then here the conditions will be subject to summation aij xj. Okay, and whatever the inequality is there, greater equal b I, where j is running from 1 to n, yeah, and I is 1 to up to m, and the non-negativity conditions are there, that is xj is greater equal 0 for j running over 1 to up to n. Now this is the compact way of writing the general LPP. The same LPP can be again represented in matrix notation as follows. Okay, notation. In matrix notation we represent the LPP as, say, optimize, that will be either maximization or minimization. Okay, where z equal to c times capital C times x. Now how is c represented? C is basically your, I'll write like this. It is a small c, but it is a vector. It's a vector 1 cross n, and x is n cross 1 vector. Okay. Then here you have subject to. Now there is a big matrix here, ax, which is here ax. So A is an m cross n matrix here, m cross n into x into n cross 1, which is less equal or greater equal the matrix B. Okay, the small b matrix, you can label it with m cross 1 conditions. Okay, that way. And there are those non-negativity conditions are there, that you can also say it is that x is greater equal n cross 1, which is greater equal 0 vector. Okay, or a matrix you can call. So what is a, z, c, everything, let us see. So C matrix, which is 1 cross n, is going to be all those coefficients c1 c2 up to cn. So this is a 1 cross n matrix. Then here you have your x n cross 1 matrix, which will be x1 x2 so on up to xn. Then here am cross n, this matrix is a11 a12 so on up to a1n. Then this is a21 a22 so on up to a2n. Then finally you have am1 am2 up to amn. Okay, this here. And the B matrix, which we wrote as n cross 1, you can label this as capital B also, but since we have used small b, I'm just using the standard pattern which is there in simplex method. So here it is b1 b2 up to yeah, bm, right? Bm here we have. Okay, now all these matrices that you see, they have some name. So what are the name over here? The first name I'll give you here is this. A is called the coefficient matrix. Okay, this matrix is called the coefficient matrix. Then x is the vector, you can call it, and so this is called decision variable vector. Decision variables are, these are all x1 x2 xn are decision variables, so you call it as decision vector. Okay, then B is the constraint on the matrix that you put, like all the condition restrictions, these are basically, or they are also called the requirements. So how much is the limitation for that particular constraint or whatever you have, your LPP. So what you do here, you call this B matrix as the requirement vector. Requirement requirement vector it is. And C is the C vector is sometimes it depends. Now see, if it is maximization, we always need to maximize our sales. It is always we are interested in maximizing our profits, like that. Okay, so it depends what it is. So generally it is the cost or the price or profit vector, something like that we call. So this one is cost or maybe let's say price or profit vector. Okay, there is no fixed name for this, it depends, it keeps on changing as per the question to question. We generally called it as a cost coefficients, but then it is not a big problem, then you can handle it. And the zero that you see, this is the zero matrix. Okay, this is zero matrix of order n cross 1. This is all the basic formats that we need in order to understand what is the general form of the LPP. Now let us go in detail and understand what will happen to the canonical form. Now mostly whenever we deal with LPP, we always deal with the maximization type, because it is the most standard way to understand the LPP and help out our understanding to become strong. Because once you understand maximization type, automatically the minimization type is taken care, because there are some simple rules are there that help us to understand it easily. Okay, so we'll understand what is the maximization type of a problem and how it works. Okay, so we understand here canonical form of LPP when we want. So we take up here maximize we'll take a maximization type, minimization type will be understood automatically. Okay, so maximization, when we do, so what we will write here is this. So in maximization of objective function when we want to do, so we will write here max z, which is c1 x1 plus c2 x2 plus and so on up to cn xn. Then we write here subject to the constraints, to conditions we say, or constraint, subject to conditions. The first condition is same, a11 x1, a12 x2, so on up to a1n xn. Now we always, when we want to do maximization, we always see to it that our inequality is of less than or equal to type. Okay, so that is what is the first understanding that we have to remember. Then every inequality should be of the type less than or equal to. So x1 here we have, then here a22 x2, so on up to a2n xn less than or equal to b2. Then here a mn x1 plus am2 x2 plus and so on up to a m n x n less than or equal to b m. Okay, so all these formats are there. And finally we have the non-negativity conditions, which are x1 x2 up to xm greater equal to 0. All of them are greater equal to 0. So this is the maximization type of question for canonical form. When we consider canonical form, meaning the natural format in which the LPP is written. So whenever we are considering the maximization type, we always want our inequalities to be of the format less than or equal to, okay, the main conditions which are there, they all should be of the type less than or equal to. Okay, so let me give you all the features here. Okay, the first is the main feature here, that is the main feature here, what we saw is that first thing is objective function is of maximization type. Then second thing is that the most important thing is all constraints, all conditions have to be of this type, okay, less than type, okay, except non-negativity, except non-negativity activity conditions. Okay, that is one thing. And except the that thing that we is the most important. And the third thing is that all decision variables are non-negative. Okay, all decision variables are non-negative. That is what we need to know. Now one very important thing here you can consider. So suppose if someone has asked you what is the minimization version of this, so in that version what will happen is you will have the same thing, but suppose something is of um, you know, like minimization is asked, you take the negative of it and you will get the maximization of the answer. So I'll not deal it right now, but I'll just told you, I'll give you that note over here. Let me give that note here. Let's suppose minimization of z is given to you. It's a c1 x1 plus c2 x2 up to cn xn. This is given to us. Then it its equivalent is maximization of minus of z. If we say, then all these terms will become negative. Minus of c1 x1 minus c2 x2 minus and so on up to minus cn xn. Okay, so this is what is meant by equivalent thing that you need to do. So Now we now we consider here another inequality, that if any inequality is of greater than equal to type, okay, if any equality is of greater than equal to type, then we convert it to less than type. We convert it to less than equal to type by multiplying -1 on both sides. For example, if we are given, let's say 6x1 plus 5x2 is greater equal 10, then we convert it to, uh, if the question, depending upon the question, right? Firstly, if the question is of maximization type, then we will convert it to minus of 6x1 minus of 5x2 less equal minus of 10. This is how it will become. Okay, now uh, there is some very important thing is there. One very important thing here comes, if there is a equality there, how to handle. These were inequality, but if equality comes, then how to handle the equality. So this is vi very important part. This is very unusual here. So an equation may be replaced by two weak inequalities in opposite direction. So I'll give you here an equation may be replaced by two weak inequalities in opposite directions. Like, for example, if we have, let's say, the same one, 6x1 plus 5x2 is equal to 10 is given to us, then we will say that this is a combination of the following two, that is, it is same as 6x1 plus 5x2 less equal 10 this way, and 6x1 plus 5x2 is greater equal 10. This is one way to say. Okay, first way, this is the first way. Let's say I'll call the first way, or we can say like this, or we can say this can be done as 6x1 plus 5x2 is less than 10, and minus of 6x1 minus of 5x2 is less than minus 10. That's another way around. So it depends how do we replace it? Okay, so here is the second way. Now the next part comes here, that suppose another important condition is here, that the fourth condition, suppose that we have a condition of the form, let's say 6 modulus is there, 6x1 plus 5x2 mod less equal 10. Okay, if this mod is there, then this mod sign gets replaced with two inequalities. Okay, so the first one would be, so this is equivalent to say that it is 6x1 plus 5x2 is less than 10, and 6x1 plus 5x2 is greater equal minus 10. This is one thing we do. Now another way around, if is something like this is there, that this is the case 1, if you have either this kind of thing is there, this is case 1, and suppose case 2 is there something, let's say that they have given to you as 6x1 plus 5x2 under the modulus is greater equal 10, then the whole thing will change here as 6x1 plus 5x2 is greater equal 10, and here you will have 6x1 plus 5x2 is less than minus 10. That's how it will go. This are this is one another important case that we have here. So now we will take up this one here. The fifth case that we will have is that suppose all of the decision variables, like some are free variables, some conditions are not there on sometimes on all decision variables. So suppose that all decision variables are not non-negative, but some are unrestricted. This is the word unrestricted. Suppose some are unrestricted. Okay, so it means that they are either positive, zero, negative, we don't know. So in such a case there are no constraints are there on them. Okay, some are unrestricted, that means unrestricted, or you call them unconstrained. Then in such case we express those variables as the difference of two non-negative variables. So consider like this, that if you have here in LPP, in LPP x1 is greater equal 0 and x2 and x3 are unrestricted, then what do we do here? We would say let x2 equal to, I'll express it as some another variable. Let me call it as, let's say, I will need two more variables, let's say y2 and y3. Okay, I'll take y2, y3, I'll take, and I'll express it as a difference of this. Okay, y2 minus y3 here, I'll express it here as greater equal 0. I'll make it, uh, I'll express rather here Ex let x this one, and x3 I'll express as, let's say, y4 minus y5, and then I say y2, y3, y4 and y5, they all are greater than or equal to 0. So all the variables, now how many variables I will have? So I'll have, therefore I will have x1 which is already greater equal 0, and now the additional ones which I added, y2, y3, y4, y5, all these extra variables which came into the picture, they all will be also greater than or equal to 0. Okay, okay, so all these conditions which we saw right now are there when they can come into an LPP when a question is given to us. Okay, I just started with a basic theory over here to help you to understand that this is a general and the basic LPP when it is seen. So maximization type is the very standard and the most easiest one to begin with, but when you begin over here itself, there are case that start coming to the mind, that is like the theoretical cases these are, and in practical they are very useful. So we clear out all the cases in the beginning itself. So first thing, let us recall now again, when we are doing maximization type, first thing that we have to remember that all the conditions should be of less than or equal to type. Okay, that is the main thing. And if us we want to have this minimization, we can do this negative of the maximization. All the types we can convert also from greater than sign to less than type by multiplying by -1. Yeah, this is very important. If there is an equality, we can change it by uh, taking it as a greater than or equal to and less than or equal to sign, and accordingly we can adjust what type of inequality we want depending upon the objective function, whether it is maximization or minimization. Yeah, the condition, there can be an absolute value also in the condition, so that we also saw here. How to handle unrestricted variable also we saw. So unrestricted constraint or unrestricted variables are there, then how to do over here. So this is one very important thing. Now the final thing that I'll give you in the theory is a note here, that the first important note that we need to do is that a minimization problem a minimization problem can be in canonical form, okay, if all its variables are non-negative and conditions or constraints are of greater equal type. Okay, so this is one very important thing. So only thing in that case, what will happen here is this. I'll give you here, that is, we have to minimize z such that it is c1 x1 c2 x2. Here you have this minimization, here cn xn, the objective function we are minimizing. Maybe it is a cost function, or maybe it is you are trying to reduce any quantity which is there to be in the real world, that you are trying minimize your losses or something like that. So subject to condition, that is a11 x1 plus a12 x2 plus and so on up to a1 n xn. Here all are greater equal b1. Okay, all the inequalities will be greater, a21 x1 a22 x2 plus and so on up to a2n xn greater equal b2, and so on up to a mn x1 plus a m2 x2 plus and so on up to a mn xn greater equal bm. Now this is what is the standard format of the canonical form. Okay, so here you will have the conditions, that is x1 x2, all these conditions xn are greater equal 0. Here everything is greater equal, only in maximization the conditions are less than or equal to type. Okay, so now let us understand what is the whole thing here. Now in order to convert any maximization question to a standard form, we need to add slack variables over there. The slack or the surplus variables are there into the picture. Now what are they? Let me help you with them. So these are some terminologies that come into the picture. So I'll just explain you with the example, and that will be very much clear, and no doubt will remain there. Okay, so let me help you here. Suppose here what I'm just explaining what is called slack variable, slack variable and surplus variable. Suppose we have some condition that here it is let's say 6x1 plus 7x2 plus 4x3 is less equal 11. Suppose some condition is like this, then we convert it to equal to type. Okay, then converting it to equal to type, to convert it to equal type, what do? We add, so this will become 6x1 7x2 plus 4x3. Now this here you add the variable. Let's say I'll add here s1. Okay, add s1, which is just a arbitrary number, so that when you add up it equals 11, something like that. Okay, so when you made it equal, that by adding, when you did it, it is called slack variable. Okay, so here this variable is called slack variable. Slack variable. Now what is a surplus variable? Let me help you out. So surplus variable, so suppose you have again 6, I'll take another equation. Let's say 9x1 plus minus 10x2 plus 11x3 is greater equal 400. Suppose some condition is there like this, then what do you do here? Now the LHS is more than the RHS, right? So in order to make it equal, what we do is we subtract. So to convert it to equal type, nine x1 minus 10x2 plus 11x3. Now what you do is you subtract here minus s3. Okay, you subtract it by making it here minus s3, and this will give you the answer which is equal to 400. So when you subtract it and it becomes equal, so this variable is called surplus variable. Okay, this variable is surplus variable. It is, see, surplus variable and slack variable together are called admissible variables. Okay, so I'll just give you them. They are also called as admissible variables. Admissible variables. So this is the basic thing that is very much important while understanding the what you call this LPP terminologies, because these terminologies, if you once get comfortable, then all the foundation is going to go smoothly, because LPP as such, if you see, it's a laborious task. Okay, the sums are going to be little lengthy in nature, so we have to understand them step by step. So now we are in a position to understand what is the standard form. So a standard form of LPP, standard form standard form of LPP. So standard form of LPP, let us see. Whether it be a maximization type or a minimization type, okay, you have to now write the whether whether the LPP is of maximize max max I'll just write here maximization type or minimization type type all the constraints all the constraints must become must be made equal to type by adding slack by adding or subtracting whatever by adding slack or surplus variables. I mean adding or subtracting also will work, okay? Adding, subtracting slack variables. Now let me help you out what it is. So adding all constraints must be made equal to type by adding slack or surplus variables to obtain the standard form of LPP. So let us see how to handle here. So let's see, for example, we'll take up now a question. So a lot of theory we saw right now, so we will take up a question here. So first question is, let's say express the LPP into the standard form okay. So what will happen into the standard form, let us see. So the standard form, the question here is maximize max z is equals to 7x plus 5y subject to 2x plus 3y less equal 20, and here it is 3x plus y greater equal 10, and x and y both are greater equal 0. So how do we first convert it to standard form? So firstly we write here, first the conditions we will see. So conditions, we will have to introduce slack variables or surplus, both we will have to introduce, okay? So what we will do here, uh, that we need to make it a standard form. We will not convert in though it is maximization type, and here they have asked us that we told here that all the maximization questions should be of less than or equal to type, we need the inequality, but it's not a problem when you have to write the standard form. You just have to remember that you need to add or subtract the variable. Right now we are not into what we call here basically that we are not pushing ourselves to, you know, just to write the we are not going for solving of it right now. So currently we will see how to handle all these things. So here when we are writing the maximization type question, so first we say maximize z. Now see, when we maximize z, we have 7x plus 5y. Okay, this is one thing. Our question should be of no change. Maximization is our objective. That is our objective, that so there should be no change into it. But I will help you out how to handle it. So now subject to the condition. So the condition subject to the condition is 2x plus 3y. Since it is less than type, so I will add a slack variable. So I add s1 over here and make it 20. The next I'll add s1 and make it 20 equal to 20. The next here it is 3x plus y is greater than type, so I subtract a surplus variable here and I'll call it s2, which is equal to 10 here. Now I added two variables. Okay, so these two variables are also going to be non-negative, so they are x and y, which are already there, and s1 and s2 which I added. They all these four variables are non-negative. Now I have to reflect s1 and s2 in the objective function. So what I can do, objective function should remain unchanged. So what I'll do here, I'll put two new terms but with their coefficient 0. So 0s1 plus 0s2, no change, because they are slack variables and they are now not affecting my objective function at all. Got that? So let me help you out with one more example in this kind. Let's take like this. So this is the standard form. This is the required standard form of LPP. Okay, the next one, let us take up another question. Write the standard form of LPP. So let's take maximize z equal to 3x1 plus 5x2 subject to three x1 plus 2x2 is less equal 15, 2x1 plus 5x2 is greater equal 12, x1 x2 greater equal 0. Again the same thing. In order to write the standard form, we will write here the standard form of LPP is, we first write maximization of z with no change. Okay, so 3x1 plus 5x2 no change, subject to now the condition is 3x1 plus 2x2. Okay, and it is less than type, so less than, when it is here less than, so I will add a slack variable here. So it is s1 equal to 15. The first condition, you use the first variable s1. Now the second one is 2x1 plus 5x2, so there is a surplus here, so I'll subtract s2 and I'll write by s2 equal to 12. So what I'll get here, x1 x2 s1 and s2 greater equal 0. So this is the standard form. Now again, as I told you, there should be no change in the standard form of the uh, objective function. So let us write here, s1 and s2 are also the variables, but they are not going to affect our calculation of z. So what we do here, 0 s1 plus 0 s2. This is how it is here. Now let me help you out with an unrestricted question. Let's take up another example in which something is there and something is not there, and half is upside down and it might be tipsy a bit. So let me help you out with that. How do we handle this? Then all these things are very important. So question 2, question 3 we take. Here we take, let's say, express LPP in standard form. Now things are going to be little bit difficult, so because we are now moving to something called a unrestricted case. Okay, so LPP in standard form, so maximization of z is there. Here it is 3x1 plus 2x2 plus 5x3 subject to. Now conditions are many. 2x1 minus 3x2 is less equal 3. x1 plus 2x2 plus 3x3 is greater equal 5. 3x1 plus 2x3 is less equal to, and x1 x2 both are greater equal 0. There is no mention about x3. So we must understand here that whenever x3 is not mentioned, if a variable is not mentioned in the question, that means it is a free variable, it is unrestricted variable. So here we'll note down here, note that nothing is mentioned about x3 in non-negativity condition. Okay, it means that x3 is unrestricted. Please remember this. This is very important. When nothing is mentioned, it means it is unrestricted. So now let us maximize this. So first we write here, first we now understand the condition and then we go for writing maximization, because now there is slack variables are going to be there, but we have extra variables going to come into the picture. So we first write, let x3 get replaced. Generally, see, whenever we replace a particular variable, we don't replace it by a entirely different alphabet. What we do is this way, we write it like this way, that x3 is equals to x3 dash minus x3 double dash. This is how we write. So it helps us to remember that we have the same number of things are there, but in a different way. So we remember that this thing has happened for x3. This is how it is generally written. Now see, because we did x3 is replaced here, x3 dash minus x3 double dash, okay, so our maximization question will change now. Because there were slack variables, that was okay, but now we have done a change in x3. So the main question, maximization of z, the objective function will have a change. Therefore max z will be 3x1 plus 2x2 plus 5 times x1 x3 dash minus x3 double dash. That will happen, okay. And now what happens to the condition? So the condition now is subject to 2x1 minus 3x2 less equal 3. This is what we will have, and after this we will write the condition for the second one. Now the second one had x1 plus 2x2 plus 3 times x3 it was there, right? So 3 times x3 will now change to x3 dash minus x3 double dash greater equal 5. No change. We will not add slack variable immediately because we are just changing the question because of the unrestrictedness of the x3. So here that is what happened. The next one what we do, there is again x3 is there, so we change that part also. So here it is 3x1 plus 2x3 is now going to become x3 dash minus x3 double dash, which is less equal to, okay. And now what do we write about non-negative conditions? So x1 is greater than equal to 0, x2 is greater equal 0, fine. But what about x3 and x3 dash and x3 double dash? Now there is no longer x3 into the picture, so it is x3 dash and x3 double dash, they both are also greater equal to 0. This is how we have. Now we convert our question to standard LPP. So standard form of the LPP, therefore the standard form of LPP is, we now first always write the condition. So here it is maximization max z, not a problem. Here you will have 3x1 plus 2x2, okay, plus 5 x3 dash minus 5 x3 double dash, that is there. And then subject to here it will be 2x1 minus 3x2 plus, we will have to add one slack variable over here, so that is s1, okay, which is making it equal to 3. The next one, because here the second inequality is greater than, so here it will be x1 plus 2x2 plus, now see this 3 I'll multiply it inside to each of the term, so it is 3x3 dash minus 3x3 double dash, and now greater than is there, so minus of s2 equal to 5, okay, equal to 5. And then there will be next one will be 3x1 plus 2x3 dash minus 2x3 double dash, and then here it will be plus of s3 equal to 2. So this is what is there. Now how many s1, s2 and s3, three variables we added, so we can add them in the objective function also. So 0 s1 plus 0 s2 plus 0 s3, if you add it, no problem. If you don't add it, still no problem, because maximization of the function, the optimization of the function should not get changed unless there is some unrestricted variable. Slack variables or surplus variable do not affect your main part of the objective function. Okay, so their coefficients are always 0 over there. So 0 s1, 0 s2, 0 s3. So here we have this, and what the non-negativity conditions will be x1, x2, x3 dash, x3 double dash, s1, s2 and s3, all these are greater equal 0. So this is what is the standard form of the LPP. Okay, so let us see one minimization type of question and then we can stop. Or we will also have to see one equality constraint question, so that will help us to understand how to handle all these conditions, and then we can stop in order to understand. If there is any different case, then we can handle it in the next class also, next video lecture. Yeah. So here I'll just deal with better would be an example I'll take up is of minimization type. Yeah, so let us see here. So this example is of question number after 3, question number 4. Okay, so question number 4, let's say it's minimization. Express the following LPP into standard form. This will be a slightly different and a difficult understanding, so let me help you why and how it is going to work. Okay, let me help you how does this thing work now. Minimization, minimize z is equals to 2x1 plus 3x2 subject to 2x1 minus 3x2 minus x3 equal to minus of 4. 3x1 plus 4x2 minus x4 equal to minus of 6. 2x1 plus 5x2 minus of x4 equal to minus of x5. Plus of x5 sometimes this is erroneous. Yeah, plus of x5 equal to 10, and then here it is 4x1 minus 3x2 plus x6 is equal to 18. So here you have where x3, x4, x5, x6 are all, right, I'll just say that greater equal 0. Now they have not mentioned anything about x1 x2, so it means that your x1 x2 are unrestricted. Moreover, what is special about this question, that question is of minimization type, but everything is conditions are all equality. So how to convert it to standard form, and how do we understand that what variable is going to be what? Okay, so how to add slack variable, because we want equal signs, already we have got equal, so we cannot have slack variable nor we can have surplus variable. So in this case what is going to happen, so I will explain you what is the difference here. Let me just guide you upon this, and then we can move on to the next example for understanding. So um, what is very important in this case is that first we understand here that x1 and x2 are unrestricted. x1 x2 are unrestricted. Okay, this is first thing to be noted. Second thing, all conditions are equal type. All conditions are equal type. So now how do we handle here? All this. So first important thing is that we will replace x1 and x2 here by a new variable. Let's say we will label it as because already there is this here, so let's say we'll write here let x1 is equals to x1 dash minus x2 minus x1 double dash, and x2 we will replace it by x2 dash minus x2 double dash. Okay, so for the main question, what happens now? So the question is of minimization type, so minimize here z as we will have 2x1 dash minus x1 double dash plus 3x2 dash minus x2 double dash. Okay, after that what about the condition subject to condition? The conditions are now, I'll write here the condition in this way, that is 2x1 2 times x1 dash minus x1 double dash plus no, not plus, there was minus here, right? There is minus 3x2. So we'll write here minus 3x2 dash minus x2 double dash minus x3 equal to minus of 4. Then here it is 3x1 dash minus x1 double dash plus 4 x2 dash minus x2 double dash minus of x4, which is equal to minus of 6. Okay, and then here we have 2x1 dash minus x1 double dash plus 5x2 dash minus x2 double dash plus x5 equal to 10. And here it is 4x1 dash minus x1 double dash minus 3x1, no, not 3x1, it is 3x2 dash minus x2 double dash plus x6 equals to 18. Now here we got all these conditions that we wanted, and now how do we handle the terms? Okay, so we have another thing here, that is all this x1 dash x2 dash x1 double dash x2 double dash x3 x4 x5 and x6, all these are greater equal 0. So how many variables? These are 4 and these are 4, so there are in all 8 variables are there which are greater equal to 0. So here now we also note here that these are two terms which are negative. Okay, the conditions are negative on the right hand side, so it is always advisable that you have a right hand side to be positive, so you shift the minus sign on the other side. So what you do here, in the next step you can change them and write here that maximization we will do, sorry, minimization of z which we are doing. So all the same things will be there, but what will happen is, okay, all this thing is here, um, we will paste it here. Yeah, so what you do is convert these signs to positive. So what will happen is that making them positive, here you will get minus of this, and then there will be plus, and then there will be plus, here there will be minus, and so here this will change to minus, and here it will be plus. So all this shifting that we will need to do, and now finally we can write all them with their coefficients here. So you can remove these brackets also later on, and then you write each variable with their coefficient. So that is, we can write here the conditions, that is they change to subject to the same function will be there. The same function you can keep, minimization, that is minimize z equals to 2x1 dash minus 2x2 dash, sorry, 2x1 double dash x1 double dash plus 3x2 dash minus 3x2 double dash. Okay, and then here what we did, we will just write that subject to constraint, it is minus of 2x1 dash plus 2x1 double dash, right, plus 3x2 dash minus 3x2 double dash plus x3 equal to 4. Then minus 3x1 dash plus 3x1 double dash minus 4x2 dash minus plus 4x2 double dash plus x4 equal to 6. Then here it is 2x1 dash minus 2x1 double dash plus 5x2 dash minus there will be 5x2 double dash plus x5 equal to 10. Okay, and then here you will have the same conditions, that is 4x1 dash minus 4x1 double dash minus 3x2 dash minus plus here 3x2 double dash plus x6 equals to 18, and the same condition x1 dash x2 double dash x sorry, here there will be non-negative conditions are, and x1 double dash x2 dash x2 double dash x3 x4 x5 x6 greater equal 0. Now one very important understanding over here would be that where did the condition for slack variable go away. So here if you observe carefully, x3 x4 x5 and x6, they were already mentioned in the question as greater equal 0, and they are not affecting the minimization function, objective function. They are not there at all, right? They were not there. That means the variables which are not there in the objective function but they are already there in the constraint, they are acting like slack or surplus variable. Getting that? Okay, so they are the slack variables. Okay, so here note down here note that x3 x4 x5 x6 are behaving as slack or surplus variables as they are not in the objective function. So this is one very important thing on my side for this kind of question. So I hope you followed this basic lecture of LPP. I know it was a very lengthy lecture and a very long one, but all these conditions that I gave you today are going to help you to understand the topic in detail. This was the basic foundation lecture, and I always prefer my foundation lecture to be the detailed and to be the, you know, the precise all notations and everything to be given to you at one go. So this will form your basis all throughout. Okay, I hope these examples help you all throughout and you will be able to understand the topic nicely. Thank you. I'll see you in the next part of the LPP.